So, corresponding to each element of SO3 you have 2 and exactly 2 elements from SU2 which map onto this element here. It is a 2 to 1 homomorphism, and these two matrices in SU2 differ only by a sign, overall sign. So, several things immediately emerge. So, you got SU2 here, this is the group SU2 if you like, it is a connected group, it is connected, and the reason I say it is connected is because the parameter space is a space of 4 real numbers satisfying this condition. And what sort of object is that? It is a hypersphere, it is a 4-dimensional sphere, right, it is the surface S3, it is essentially S3, it is a 3-dimensional object denoted by S3. Just as S2 is the surface of a balloon, it is a 2-dimensional object, S3 is the higher dimensional analog of that, and it is a connected object, this guy here. Not only connected, it is a simply connected object. You can go from any point on it to any other point without leaving the space. Every closed loop on this space can actually be shrunk to a point without leaving the space. There are no holes in this space, no handles or anything. So, this is very important that this is a simply connected space, the parameter space here. But right now we are interested in the homomorphism from that to SO3. This too is a connected space because the disconnected part of it, the ones with determinant -1 do not exist in this set here, they do not, that is the other part, the improper rotations. This is the proper rotations in 3 dimensions with determinant +1, they are all continuously formable, obtainable from the identity by a sequence of infinitesimal transformations. So, it is a connected space alright, and this space is parameterized by n and psi, and this space is parameterized by the same n and psi appearing in different combinations so as to form a matrix of this kind. Because I just wrote down what this matrix was, I said all you have to do is to take e to the I sigma dot n psi over 2, write it as a 2 by 2 matrix, and that is this. You can verify that it is an SU2 element of this kind, okay. But the space is connected here and simply connected, and we have not yet seen what the space there is going to do. But what we do know is that for every element here there are 2 elements that are mapped onto. In particular, the identity element I is a 3 by 3 orthogonal matrix which corresponds to no rotation at all. So, it is a 3-dimensional, let me just write I sub 3 to tell you, it is a 3 by 3 unit matrix, that is no rotation at all. That would correspond here in SU2 to both the 2 by 2 identity matrix as well as minus the 2 by 2 identity matrix, because both these fellows would be mapped onto this identity element out here. So, this is called the kernel of the mapping. This set I2 minus I2 is the kernel of this homomorphism which takes you from this group to that group, okay. It is the set of elements which map onto the identity element in the other group, okay.
There would be a map from this I2 minus I2 to minus I3 also, would it be? Minus I3 there.
Minus I3 is not part of this set, right. Minus I3 would mean the determinant is -1, but this is the connected group of all those rotations with determinant +1, proper rotations, right. So, this map does not do that, does not take you there, okay. This thing here, there is another structure to this a little more, and that is these two themselves form a group, I2 and minus I2, namely the 2 by 2 unit matrix and minus the 2 by 2 unit matrix, they form a group by themselves, a group of order 2, because the product of I2 with I2 is I2, I2 with minus I2 is minus I2, and minus I2 with minus I2 is plus I2. So, it is a cyclic group of order 2. It is isomorphic to the addition of integers modulo 2. You can put all the odd integers in one bin, all the even integers in one bin, and under addition even plus even is even, even plus odd is odd, odd plus even is odd, and odd plus odd is even.
Again, so how come this minus I2 is a part of SU2, shouldn't the determinant be -1 for minus I2?
-1, it's a 2 by 2 matrix, right. So the determinant is +1, right. So it's very much in SU2, but that's the whole point, that because this is even, these two fellows are sitting here, but they both map onto the identity transformation there, right. So if you put I2 on both sides and put r dot sigma in between, you are going to get r dot sigma, whether you put plus I2 on both sides or minus I2 does not matter, right. Since these two fellows form a group by themselves, the technical way of saying this is that this group SO3 is isomorphic not to SU2, because isomorphic would mean one-to-one connection, but isomorphic in the sense that it is SU2 up to a sign, So what it technically is called a quotient group. This is SU2 quotiented with this cyclic group of order 2. So up to a sign, this is modulo this Z2 element here, okay, and these two are now in one-to-one correspondence. So if you ignore the sign of the matrix, overall sign of the matrix in SU2, and regard both the plus sign and the minus sign as going to one element, that quotient group is the same as SO3. There is this 2-to-1 relationship, and this is the technical way of writing it, that it is a quotient group, okay. This is actually a coset space, it is the set of coset space of left cosets of Z2 in SU2, but since this is a proper subgroup, in other words you take any element of SU2, let us call it G, and then you act on this Z2 and do Z inverse here, you end up with the original thing, because this is just identity or minus the identity, and it is a normal subgroup, this guy here. It is called the center of SU2. It is the kernel of the map in the sense that those elements map onto the identity element under this homomorphism. So this quotient group, this structure makes things very interesting. It says that locally in the neighborhood of this identity, it will look like the neighborhood of this identity here, locally, but the global topology of this space and that space can be very different from each other, as we will see. Locally this is going to look exactly the same, but globally this is very different altogether. It is like you have a torus and you know that the actual curvature on a torus is 0, but of course you do not realize it. Locally of course it will look quite flat, but then as you go around you realize the global topology, there is a hole in the middle, etc. Now let us see what the parameter space of SO3 is going to look like, okay. And that is going to be a little non-trivial. Yeah.
So the SO3 group is simply connected.
Pardon me?
The SO3 group is simply connected.
No. No, it is connected, but we will see that it is not simply connected.
But from the identity through infinitesimal rotations, we can build all elements, right?
Yes,
But,
but yet it is not simply connected. We will see how, precisely, exactly. So locally the thing looks like the topology of, it looks like S3, but globally it will not, okay. So it is clear that once you do a complete circuit in a special way, there will be something funny going on, and we will see what that is. Now how do we parameterize that space? There are 3 numbers, so we should be able to parameterize it by 3-dimensional space, right. Let us see whether we can do this. The first number is n. This is actually a set of 2 numbers, it is a unit vector. Now n can be parameterized by points on a sphere. You can simply say latitude and longitude. Once you specify on a unit sphere, you have specified n altogether. So let us say that with respect to some given reference frame, the direction will specify n, and now I also would like to say what is the amount of rotation in the plane perpendicular to n. I am constructing a parameter space. So let us have this convention that the length of this point from the origin gives me the psi, gives me the amount of rotation, and the direction of the point in space gives me the axis of rotation, okay. Then what is the parameter space? It is a solid sphere now, because points inside the sphere would correspond to rotations less than the maximum allowed rotation. And what is the maximum allowed rotation in about any axis? 2 pi. So what you need is a solid sphere of radius 2 pi, such that in that sphere at any point you know the direction from the origin, that gives me the unit vector n, and you know the length of this point, distance of this point, and that gives me psi. So the naive way of looking at it would be to say that the parameter space of SO3 is a solid sphere of radius 2 pi. Every point in it corresponds to some rotation. The origin corresponds to no rotation at all, the identity matrix. But you see, you do not need that, because if I have an axis like this pointing up like this in this direction, this is the axis, and I make a rotation by pi and I end up with this configuration, it is the same thing as rotating about the opposite axis through an angle pi. And let me show you that by actually drawing something on it, right. So let us make a little mark here and I put an arrow here up here, let us do that on this side. Okay. So this is the orientation after the rotation. I start like this, the arrows I can see it on this side, and I am going to rotate about this axis up here, the axis is pointing upwards, and I rotate through pi in the positive sense, and here is the configuration of this object with the arrow on this side pointing upwards. But I now rotate about the opposite axis again through plus pi. So looking from downwards I have to rotate in the positive direction, that is this, and it gives me exactly the same configuration as before. This means that I do not have to rotate through 2 pi. Because I allow an axis like this as well as an axis in the opposite antipodal direction, a rotation by pi is sufficient. This implies that the solid sphere does not have to have a radius of 2 pi, a radius of pi is sufficient. Good. Once we accept that, then here is the parameter space. Here is no transformation at all, the origin, and then the radius of this fellow is pi. If I said let us take this point inside the sphere at some distance less than pi, that would correspond to using this as the axis of rotation and this amount here as the psi, the amount of rotation about an angle about this axis n. Okay. But there is a catch to it, this solid sphere is a simply connected object, there are no holes in it, it is a connected object, it is a simply connected object. But the catch is that once you hit the surface, this point here corresponds to a rotation by pi about this direction, but that must be exactly the same as a rotation by pi about this direction, which means that this point is mathematically the same as that point, they are glued together, and that is true for every pair of antipodal points on the sphere. So it is clear that this 3-dimensional object, it has got 3 dimensions, that is for sure, we cannot write it in 3-dimensional space, we cannot, I cannot find a model of it in 3-dimensional space, you need a higher dimensional space in order to embed this object in it. There are lots of such surfaces, there are even 2-dimensional surfaces which you cannot embed in 3-dimensional space, like the Klein bottle, you can't embed it. So this is one of those objects, it is a 3-dimensional object which is bad enough, but you cannot embed it in 3-dimensional Euclidean space and make a real model of it. Okay. Imagine therefore that there is an invisible string glue, invisible string of 0 length which says that this point is the same as this point is the same as that point, etc. Let us imagine that. Okay. Now the question is what sort of, it is connected, but what sort of connectivity does this object have? Now how do you find the connectivity of any object, whether it is simply connected, doubly connected, and so on and so forth? What you do is to draw, is to map loops onto this space. Whatever space you have, you map loops onto the space and you ask, can I shrink this loop to a point with continuously without leaving the space at all? If you can, and you can do this for every loop in this space, then it is simply connected. If you cannot, then it means that the space is not simply connected, and the connectivity depends on how many different classes of such paths can you find. Okay. Well, let us take a very simple example, and now I am going to go back a little bit and give you this example, and then we will come back to the 3-dimensional rotation group. Well, the answer here will turn out to be doubly connected. There are exactly 2 classes of closed paths which are inequivalent to each other. Okay. On the other hand, let us look at a simpler example, easier to visualize because it is a lower dimensionality. Let us look at the group of rotations in a plane that has got just one generator, it is just about the origin, there is just one generator, and it is characterized by 2 by 2 orthogonal matrices, So let us look at this group SO2 represented by 2 by 2 orthogonal matrices, and a typical matrix of the kind of this kind would be cos psi, sin psi, minus sin psi, cos psi. Determinant is 1 and psi is any real angle between 0 and 2 pi. Okay. So the set of these matrices, they are all orthogonal, they are determinant 1, they form a group, the SO2 group. Now what is the parameter space of this SO2? Clearly specified by one angle which runs from 0 to 2 pi, okay, and that is just S1. So the parameter space is S1, because with respect to any reference direction, you can actually tell me this point here corresponds to the angle psi. So all the rotations here are parameterized by points on this circle, which is a one sphere, S1. Okay. So the parameter space of SO2 is S1, this we know. Now the question is this space connected? The answer is yes, you can go from any point to any point along this circle continuously, right. So it is connected. Is it simply connected is the question. So what you have to do is to take another loop, this is a closed path, and map it onto this. Okay. So you are mapping, this is topologically the same as S1. So you are finding the maps of S1 to S1, the smooth maps of S1 to S1, and asking how many ways can you do this? Well, here is one way I can do it. I can start at this point and map it to this point, and then I go around, so this map goes around and then continuously goes back. That is a continuous map, but that can be shrunk to a point without leaving the space. So anything that does not fully go around this circle, so imagine that this is a rubber tube, the inner tube of a bike, and this thing here is the rim of the cycle, the wheel, and you are trying to put this onto that, and you can stretch this as you please, but you can't cut it. Then there are ways in which you just place it on it and then you can shrink it to a point, this trivial map, right. But then if you took this rubber band and stretched it all the way around and actually made it go around once, then you cannot shrink that to a point without cutting it. So it is clear that there is at least one class of maps different from the trivial map which can be shrunk to a point, and that is the class of maps where you actually start at some point and go all the way around, where you can do it twice. This is an infinitely extensible rubber band in topology, so you can do it twice. You can go around twice, and there is no way you can change that to either 0 or 1 winds around the circle here. You could have done it in the opposite direction, because every closed path has to be, direction has to be given, has to be oriented. So you could have mapped it in the opposite direction corresponding to winding around -1 times and -2 times and -3 times and so on. So what happens then? It means that all paths, closed paths, maps of a loop onto this S1 can be put into classes, and each class is specified by the integer which says how many times does it wind around, and that integer could be anything, 0, 1, plus minus 1, plus minus 2, etc. Now the point is these classes are in one-to-one correspondence with the integers, but the integers form a group under addition, right, which means that the classes of maps, closed of loops onto this S1, they themselves form a group, and that group is called the fundamental group of the space. So whenever you look at any space V and you ask what are all the distinct classes of maps of S1 onto V, you call that pi 1 of V, and it is called the fundamental group of that space. You would ask, well, as soon as you say group, it means there must be a group composition law. How would you find a group composition law? Well, there is a way, a simple way of actually rigorously specifying what is meant by the composition of two paths. Here it is fairly obvious. If it winds around 6 times and you compose it with something which winds around 7 times, the total is something which winds around 13 times and so on, right. You can compose paths in a well defined way, and those things form a group called the fundamental group or the first homotopy group. of this space. And the statement is, if the first homotopy group has only one element in it, the identity element, it means all closed paths can be shrunk to a point, then the space is simply connected. If the first homotopy group has more than one element, it is a non-trivial group in that case. Now what is the first homotopy group of S1? By equal to I mean isomorphic to, right. We can put all the elements of this group into one-to-one correspondence with a set of integers, right. So this thing here is the group of integers Z itself. You can do this for any space actually. So let us suppose you take the surface of a sphere, a balloon, you take the surface of a balloon, that is S2, and I ask what is pi 1 of S2 equal to. So now what I have to do is to take this loop and try to map it on to the surface of a sphere in 3 dimensions. I take this loop and put it on that surface. Of course I can shrink it to a point. There is no way in which I can encircle this sphere without being able to shrink it to a point, no matter what I do. Therefore all closed paths on this surface can actually be shrunk to a point. And so what is pi 1 of S2? It is the trivial group with just the identity element, and one way of writing it is to just write it as 0, just shorthand for saying that it is a group with one element, it is a trivial group, okay. So pi 1 of S2 is 0, and it is not very hard to show actually that pi 1 of Sn equal to 0 for n greater than equal to 2. So pi 1 of SU2 is 0, okay, simply connected. I am not proving it, but you can show that pi 1 of Sn is intuitively clear is 0, okay. This is not true for S1 because pi 1 of S1 was a very non-trivial group, was this the set of integers here. Now the next question is, for instance, let us give one more example. What is pi 1 of a 2 torus? And that will immediately tell you what this whole business is about. This is the surface, we are talking about the surface of an inner tube. It is a 2-dimensional object, surface of a donut, and the question is, what is the fundamental group of this space here? Okay. After all, a torus is formed by saying I take a circle and at every point on it I associate a circle perhaps in some perpendicular direction. In this fashion, join them all together and you get this torus here. So technically the position of a point on this torus is specified by saying with respect to some reference direction in the long axis, where is it, 0 to 2 pi 1 angle, and then in a given cross section where is it with respect to the cross section, so a second angle. So it is clear that this torus T2 is essentially S1 direct product with S1. It is specified by saying 2 different angles independently from 0 to 2 pi. So topologically it is S1 cross S1. So what would pi 1 of this space be? It would be Z cross Z, direct product of 2 sets of integers, because it would say that, well, to specify any closed path on this you have to merely ask how many times does it wind round this and how many times does it wind round that, and it is specified by 2 integers independent of each other. So it immediately says pi 1 of T2 equal to Z cross Z. Now we come back and ask just a little bit more about SO2, and that is the following, and that is a valuable lesson. Yeah.
So how connected do we say S1 is?
Pardon me?
How do we quantify connectiveness?
Its connectivity is infinite. It is infinite because there are infinite number of elements. Yeah. If it had just 2 different classes of parts, I would say it is doubly connected, but this or triply connected and so on. This thing is infinitely connected. S1 is infinitely connected. But you can do the following. I said out there, what did we see? We said that we saw that a 2 by 2 unitary matrix has a determinant which is e to the I theta, and a 2 by 2 unitary matrix with determinant 1 does not have that e to the I theta, right. So in some sense you are specifying an SU2 matrix and adding on top of it an e to the I theta factor. But what is e to the I theta? It is a representation of the 2-dimensional rotation group, because the 2-dimensional rotation, instead of specifying it by an angle or a point on the circle, I could say this is a unit circle in the complex plane and specify it by e to the power I theta or e to the I psi. So instead of this matrix, and this is a valuable lesson, instead of the matrix cos psi, sin psi, minus sin psi, cos psi, which specifies an element of SO2, I could say let us associate with this rotation the complex number e to the I psi. I just associate it. With this matrix I associate that, with every such matrix I associate this number, and I use the fact that e to the 2 pi I is 1 identically. Then it is clear that there is a 1-to-1 correspondence between 2 by 2 orthogonal matrices and points on a unit circle in the complex plane. But points on the unit circle also form a group. It is a group of 1 by 1 matrices, and they are unitary matrices because e to the minus I theta is the inverse of e to the I theta. So these fellows form a group U1. U2 was fairly non-trivial, but U1 is just one parameter, and these two are essentially the same. There is a 1-to-1 correspondence between them. But then these are points on a circle, but you could say I can do something else. This space is not simply connected, it is infinitely connected. The pi 1 of this S1 is infinite, is z, is a set of integers, right. But I can do the following, I can say I take this circle and I roll it out onto the real number line. I just roll it out without slipping onto the real number line. So what does that mean? It says I start with this, I put it here, and then I roll this circle, and as soon as it hits the end of the circumference, this point start getting mapped again once again. So a point here will get mapped, for example this point will get mapped here, it will get mapped here, it will get mapped here, and so on, an infinite number of times. So it is clear that the real number line provides a kind of cover for S1, right, but the mapping is 1 to infinite number of copies, all separated by the circumference of the circle, which you can take to be 1. So this means that the space SO2 can also be written as a quotient group. This too can be written as R1, that is the real number line, modulo an integer, right. So this is in fact got this structure. Just as I wrote SO3 as the quotient of SU2 modulo as Z2, here too I can say SO2 is R1 modulo Z. R1 is called the universal covering group of SO2 because it is simply connected. On the infinite number line the connectivity is simply connected. Every closed path can be brought back into a point, right. So this guy here is the covering group and there is a theorem which says every Lie group has got a universal covering group which is simply connected, whose parameter space is guaranteed to be simply connected. Okay. In the case of SO3 we have not yet shown that it is doubly connected, we will see in a minute that it is doubly connected, and the universal covering group is SU2. Okay. And now you can see the relation between these homotopy groups. If I write what is pi 1 of this guy, this is S1 by the way. So pi 1 of S1 is Z, this guy is simply connected and it just reflects it here. Okay. Pi 1 of any discrete group is itself, as you can see very trivially. Okay. So immediately you realize that the idea of this universal covering group is extremely useful because it ignores the complications in the global topology of this group space and focuses on the portions that are nice. This is a simply connected space can be associated with it. Now let us go back and see what happens in the case of SO3 where the connectivity is actually doubly connected. Yeah.
So by a covering group, we mean matching to another group, which is
Yeah, R1 is a Lie group, Rn is a Lie group by itself, right. So this thing here is not only a space but also has the is also a group, it is a Lie group and it is simply connected.
So by covering group, we mean we require a simply.
There is a homomorphism and the covering group, the theorem is the universal covering group of a Lie group is guaranteed to be simply connected. So all the connectivity properties will come in this quotient in here. Okay. That will tell you how complicated the connectivity is. So you will see the SO3 example immediately. In SO3 what happened? The parameter space turned out to be a solid sphere of radius pi with antipodal points on the surface identified with each other. So you had this space and then the statement was that point is the same as this point. But the point just inside is not the same as that, those are different rotations. A point slightly less than pi, less than going right up to the surface would be a rotation like this, a little angle less than pi, and in the opposite direction would be a little angle less than pi, and these two are not the same. It is only if you make it fully pi that you end up with exactly the same thing. So points on the surface are identified with each other, points just below the surface are very different from each other. Now what is a closed path going to look like? Well, in this solid object certainly a path like this can be shrunk to a point, there is no problem. But you can also do the following, I start with no rotation and make a sequence of rotations and go there, but that point is the same as this, so I come back here, that is a closed path. It's brought me back to the original orientation, that is a closed path, but this cannot be shrunk to a point because if you try, if you move this, the way to shrink it to a point is to move this here and into this. So let us call this P and P prime. I move this fellow here and bring it up to here, but this fellow dodges me and goes there. So there is no way you can close this path, I mean you can't shrink this to a point. The only way I can shrink it to a point is by doing the following. I start here and go there, I come here, I go here, then I go again out, I go to Q and start here and come back, and this is Q prime. Do this. This is now shrinkable to a point because now the trick is I start moving this P towards P prime, so or towards the other direction, does not matter, but now I can regard the path as this point. I separate these two guys. Okay. Then if I start moving P in this direction, P prime moves there. I keep Q and Q prime fixed. So after a while this path looks like this. And then P was here, that got moved to this point here. And the path was from Q prime to P. I move P even closer in this direction, not P prime, sorry, this is P. I move P even closer, this fellow moves there, and each of them is shrinkable to a point and it disappears. Okay. And these are the only two paths possible, only two kinds of paths possible. Those which are very obvious closed loops and those which start at the origin and go right through from diametric one antipodal one point to its antipodal point, but a further rotation, a repetition of this will bring you back to no rotation at all, which means that there are objects in this space in the representations of the rotation group which will not come back to their original value if you rotate the coordinate system by 2 pi, but if you rotate it by 4 pi it is guaranteed to come back. This is the origin of this double valued representations, the spinor representations. Okay. we need a little more mathematics here, we need a little more to show what are the eigenvalues, what is the Casimir operator here, etc., and that is the standard thing about angular momentum algebra. They turn out to be the various representations are labeled by a little number j, which is non-negative, takes on the values 0, half, 1, 2, 3 halves, 2, etc., and those which take on integer values correspond to scalar, vector, tensor, etc., representations of the rotation group, and those which correspond to half odd integers correspond to the so called spinor representations. These objects will change sign under a 2 pi rotation and come back to the roll values after a 4 pi rotation, okay. And ultimately that is at the origin of that is at the root of spin half, that is at the root of integer spin and half integer spin, which then in turn by something called the spin statistics theorem connects up with the existence of bosons on the one hand and fermions on the other. So finally it is a property of 3-dimensional space, the parameter space here of this thing. I already wrote down the relation saying that SU2 is isomorphic, SU2 quotiented with Z2 is isomorphic, and now you see the origin of the Z2. There are 2 such paths. So we now can write of this space, by the way, this solid sphere of a certain radius pi with antipodal points connected to each other. This thing is called a projective space and it is written as RP3. That name is not important, I will just call it pi 1 of the parameter space of this group here. This is the same as pi 1 of SU2 quotiented with Z2, but this fellow is simply connected, so this is equal to Z2 itself. Okay. 2 such classes of closed paths, and you saw explicitly what these 2 classes were. Yeah.
So if you talk about the 2 pi and 4 pi rotation, the fact that there is a distinction between them is in the parameter space of these rotation groups, right? Not in physical terms.
In physical terms, it says you got to make 2 such closed paths. So what does it correspond to saying that I go all the way to pi and then come back from pi to 0? I made a complete rotation by 2 pi. And I have to do it twice.
Physically, how do you make sense of that?
No, it's just that normally if you have an object like a vector or a scalar or something, then a rotation of the coordinate axis by 2 pi brings the coordinate axis to the original orientation, but this object will not change sign, will not change at all under this. But there exist objects called spinors which change sign, and for them you have to make a coordinate rotation by 4 pi in order to bring it back to the original sign.
Does it have any relation with the z to the power half? For instance, you have to make a rotation of 4 pi.
No, not directly. No, the fact that it is a square root is not does not play a role here. No, that's not doing it. Yeah, that's one particular function of with a branch point, square root branch point, but that's not the origin here. The origin here is deep. It has to do with the connectivity of the space of rotations. It has to do with that. So we see that SO2 is infinitely connected parameter space, but SO3 is only doubly connected. Now the question then arises, what about higher rotations, rotations in higher number of dimensions, SON, okay, what would they start doing? Well, first we have tried angular momentum algebra for those objects, and then we have to ask what happens to the case of rotations and so on. The algebra itself is fairly simple, it is not hard to do, and I will write that down and then come back. But let me say directly that the space SON, the parameter space of this is much more complicated. As you can see, there are n times n minus 1 over 2 parameters for each such element. That space is also doubly connected, also happens to be exactly doubly connected. And then the next question is, what is the covering group? What is the group, the analog of SU2, what is the group that will play the role of SU2? And the answer is, that turns out to be, this thing turns out to be a group called spin n. That is the name for the group, spin n, which is simply connected. It is a group with the same number of parameters, n times n minus 1 over 2, as SON, and it is simply connected, and the quotient again is Z2. And it so happens that spin 3 equal to SU2. In this case it so happened, but that is not true for the other groups in general. In fact, the only other case where there is a connection with the unitary group, I think, is the case of 6 dimensions. So when you have SO6 here in 6 dimensional Euclidean space, then it turns out that spin 6 is SU4, the group of unimodular 4×4 matrices which are unitary, okay. But there is no connection of this kind otherwise. Oh, by the way, since we are on it, you could ask, what about the parameter space of the unitary matrices themselves? Well, let me just make one small comment on it quickly. If you have an n by n matrix, there are n squared elements, and if they are complex numbers, you have 2n squared parameters. But the moment you put in the fact that they are unitary, then UN, this group, has n squared parameters. And then if you say the determinant is 1, you put in one more condition, so SUN has n squared minus 1 parameters. And indeed we saw that when n was 2, you had 4 minus 1 3 parameters and made it homomorphic to the rotation group SO3. So the question is, what about the parameter spaces of these guys? Well, here I will just quote a theorem. It turns out that pi 1 of SUN equal to 0. That is, SUN for whatever n is simply connected. SU2 you saw explicitly were these 2×2 matrices, alpha, alpha star, beta minus beta star. By the way, what is SU1? It is a set of 1×1 matrices which are unitary and have determinant 1. It is 1, it is a trivial group, it is just 1. Because e to the I theta must be 1 and that is it, theta is 0, that is the end of it. So SU1 is a totally trivial group, but it turns out that SUN also is simply connected, and you can ask, is there a connection between these guys? Because there is, after all, a U1 sitting in between, there is an e to the I theta factor here, and indeed it turns out that SUN UN, or let us write it as SUN UN quotiented with U1. Once again, modulo an e to the I theta factor, you have SUN. So these two are connected up in that fashion. This fellow is simply connected. Pardon?
Parameter, number of parameters, UN.
Well, a general n by n matrix has 2n squared parameters, but now you impose the condition that it is unitary, and then you have 1 parameter less. You have 2n squared parameters less. We saw that in a general 2×2 matrix we had 8 parameters, but the unitary matrix had only 4 parameters. You had enough conditions to do this, right? So it reduces from 2n squared to n squared, and then you put in the condition that the determinant be 1, it reduces one more condition, a parameter to this. Okay. So the question is, the relation I wanted to point out, this quotient relation, is simply that UN is something called semi-direct product. So this is U1, and there are many ways of denoting this semi-direct product with SUN. So what is the pi 1 of this guy going to be? You can see sort of heuristically from this. This part is simply connected, it is not going to do anything. This part is same as S1, and pi 1 of S1 is Z. So this too is infinitely connected with the fundamental group being equal to Z, the group of integers itself. So one can play this game and actually ask for the fundamental groups of various Lie groups, manifolds of various Lie groups, and then from that deduce very valuable information on what the global properties of the group are. But the infinitesimal properties are determined by the generators. And now let me write down what the generators are for SON in general, you will have n times n minus 1 over 2 generators. So the general generator will be of the form j k, for example, where j and k run from 1 to n, but it is antisymmetric, so there are just n times n minus 1 over 2 independent parameters. Here, and the algebra is very straightforward. The Lie algebra looks like JJK JLM equal to a delta Kronecker delta JL JKM plus Kronecker delta delta KM JJL minus the opposite order. So Kronecker delta delta JM JKL minus delta KL. Yeah, that's it. So that's the linear combination. Okay. Now you could ask what happens to the 3-dimensional case? Well, that's exactly the same as this, except that the identification is J12, I called it J3, J23, I called it J1, and J31, I called it J2. That is because, as I said, in 3 dimensions you have 3 planes and you have 3 axes, and you can unambiguously convert it into this thing here. So that is the general algebra here. Now you can start with this point and play further games, and if instead of in 4 dimensions, for example, if you have 1 time-like dimension and 3 space-like dimensions, and instead of looking at SO4 you look at the group of Lorentz transformations, it is SO3 comma 1, then you write, instead of this delta here you put the metric tensor here and you get the algebra for the generators of the homogeneous Lorentz group. Okay. If you put in the elements here of the symplectic matrix, then you get this for the symplectic group 2n, etc., so SP2n, etc. But that is really a topic in group theory, we will not go into that. But the main points I wanted to convey were that the Lie groups have a very remarkable structure, analytic structure. They are given by the Lie algebras that generate the Lie group, generally by exponentiating these generators. The generators obey a Lie algebra which carries all the information about the group, and in general the global topological properties of the group would require you to find its fundamental group and its homotopy group, but you are guaranteed that every such group has a universal covering group whose topology is very simple, which is simply connected, and whose structure will give you the local structure of the group itself that you are talking about. Okay. And the rest takes you a little more into detail, which I do not want to do at the moment, but this will give you hopefully some little flavor of what the theory of Lie groups is all about. There is a lot more to it. One needs to understand the role of symmetry both in classical mechanics and in classical dynamics as well as quantum mechanics, for which these things serve as a starting point here. So with that I kind of will wind up and say okay, fini.